Self-driving cars need to see in 3 dimensions, but the bulky spinning laser turrets on their roofs are about to disappear forever. A silicon revolution is replacing them with tiny microchips that steer light electronically. To understand this technology, imagine throwing a tennis ball against a brick wall. If you know how fast you threw the ball, and you measure how long it takes to bounce back to your hand, you can easily calculate the distance to the wall. Since the ball travels to the wall and back, we divide the total time by 2. The formula is distance equals speed multiplied by 10, divided by 2. LiDAR does this exact same trick using light waves instead of tennis balls. LiDAR stands for light detection and ranging. It shoots millions of laser pulses per second. Because light travels at 300,000 kilometers per second, the sensor calculates the distance to surrounding objects instantly. By combining millions of individual distance measurements, the system builds a detailed 3D-point cloud of the surrounding environment, mapping the exact shape of cars, pedestrians, and roads in real time. For years, autonomous test vehicles have used mechanical spinning LiDAR. These systems physically rotate laser diodes and receiver sensors using electric motors and gears to capture a full 360-degree field of view. Think of mechanical LiDAR like a seaside lighthouse. The lighthouse has a single light bulb and rotates a massive lens around in a circle. A boat in the distance is only illuminated for a split second once per rotation. This rotating design allows a single roof-mounted sensor to scan in all directions, providing excellent 360-degree visibility to detect objects approaching the vehicle from any angle. But this mechanical approach has massive drawbacks. Because these complex systems require hand-assembled optical parts, they are extremely expensive, historically costing up to $25 per unit. Having physically moving parts makes mechanical LiDAR fragile. Constant vibrations from driving over potholes can wear out gears, misalign internal mirrors, and make the sensor highly sensitive to temperature changes. Additionally, mechanical systems are bulky. They require a large dome on top of the car, which increases aerodynamic drag, raises energy consumption, and ruins the clean lines of modern passenger vehicles. Solid-state LiDAR solves all of these problems by eliminating moving parts entirely. Built directly onto silicon microchips, it steers laser light beams electronically rather than mechanically, removing wear and tear. Think of it like transitioning from an old film projector with spinning reels to a flat-screen television. Solid-state LiDAR replaces physical spinning gears with digital, solid-state silicon circuits. Because these sensors are solid-state, they can be manufactured on silicon wafers in standard semiconductor cleanrooms. This allows us to mass-produce hundreds of sensors on a single wafer disk. This mass production scaling drops costs dramatically, from the historical $25 down to a target between $100 and $500 per sensor, making high-end safety accessible. This compact size allows solid-state LiDAR to be hidden flush inside bumpers or behind the rearview mirror, keeping passenger cars clean, aerodynamic, and completely free of bulky roof domes. There is a trade-off. A flat solid-state chip cannot scan 360 degrees. It typically scans a 120-degree wedge. To see in all directions, a car needs multiple chips. The leading solid-state technology is the optical phased array, or OPA. This chip splits a single laser into multiple channels. By delaying the light wave phase in each channel, it steers the alpha beam. To understand phase steering, we must look at wave interference. When two light waves meet out of sync, their crests and troughs cancel out. When they meet in sync, they reinforce each other, forming a beam. Imagine dropping a single pebble into a calm swimming pool. It creates circular ripples that spread out evenly in all directions. The wave energy is distributed uniformly across the entire pool surface. Now imagine dropping 10 pebbles in a straight line. If you drop them at slightly different times, their ripples collide. By changing the timing of when you drop each pebble, you can control the waves. In some areas of the pool, the ripples meet out of phase, their crests and troughs canceling each other out, leaving the water completely calm and flat. This is destructive interference. But in one specific direction, the ripples line up perfectly in phase, their crests stack up to create a single giant wave. By changing the timing of the pebble drops, you can steer this giant wave. On an OLED chip, the pebbles are emitters, and the timing is adjusted in nanoseconds by phase shifters. This allows the laser beam to sweep across the road near instantaneously without moving parts. However, OLED chips face a major challenge: grading lobes. These are unwanted ghost beams that form alongside the main laser, which can distort spatial mapping and distance tracking. To eliminate grading lobes, the light channels must be spaced less than half a wavelength apart under 1 micrometer. Pushing fabrication limits to this nanometer scale is extremely difficult. To navigate safely, self-driving platforms use a suite of redundant sensors to back each other up, splitting tasks across 3 main pillars: cameras, radar, and LiDAR. Cameras read traffic lights and signs but struggle in glare. Radar sees through fog and snow but has low resolution. LiDAR accesses the measuring tape, mapping exact 3D shapes as the ground truth. By lowering sensor costs to under $500, solid-state LiDAR eliminates the trade-off between cost and safety, allowing advanced 3D mapping to be built into everyday consumer cars. Transitioning from bulky mechanical domes to tiny silicon chips makes the future of transportation safer and more affordable. Thank you for watching Layman's Field. We hope to keep bringing knowledge for everyone.